Okay, everybody. So we are going to be covering section 5.5, part 2 today. So in the previous lecture, we did cylindrical coordinates, and in this lecture, we're going to be doing triple integrals in spherical coordinates. So this is just the second half of that section. Okay, so as it says here, part 1 we did cylindrical. This lecture, we're going to do spherical coordinates. So I think we should just go ahead and jump right in. If you didn't look at the first lecture for this section, I recommend that you do so. All right, so let's look at spherical coordinates to get started. So let's just drag a picture over here. Uh, Maybe put it in a better location or not. Why can't I? Okay, now I can. So this is just a picture showing us what spherical coordinates are, reminding you. So we have this angle down here that we call phi or phi, depending on how you like to say it. You'll see people write it like that, which is kind of what they've got right there. And also you'll see that symbol a lot, just depending on the typeface, the yeah, just depending on the typeface. So this actually, like, this is the book um, from your book, and they also use this symbol in print. So they're almost the same, but not quite. So you should recognize them as the same. So you have that angle, which measures from the positive z-axis, and then you've got theta, the same theta that you use for polar coordinates, and then you've got this rho for a radius. So we use r for the radius in polar coordinates. We use rho for the radius in spherical coordinates, right? So we already went over those, so we aren't going to go over them again, but we'll just say rho is going to be, um, distance from 0, 0, 0 to the point. Then you've got angle phi or phi. It's going to be the angle from the positive z-axis to the I'll say ray, connecting the origin to the point. In each case, when I say the point, I'm talking about this point. And then you've got theta, which is going to be, the same as polar coordinates theta. Okay, so those are the variables that you have for spherical coordinates. We want to just briefly go over, where we're going to get a volume integral from. Um, but before we do that, I think I want to get the kind of a reminder of what our conversion factors between all the variables are. I've got one, I think, here. Hold on. There we go. Oh, I'm going to have to put that down here because it won't fit. Will it? I'm going to try. Drag up, drag down, drag down. All right, good enough. Okay. Sorry about that. You can't see exactly what I see, so that might have been easier for you here. Okay, stay now. Don't move. Okay, so here we have our conversions between spherical and rectangular. So you have a complicated formula for x, for y, for z. We also have rho is x squared plus y squared plus z squared, similar to the one for polar coordinates, but now with a z. You still have tangent theta is y over x. That's because the theta hasn't changed. And then you've got this one for phi, v, is arc cosine of z over, looks like rho. Um, so those are the relationships. You can see more of them down here that we might use in various circumstances. I'm not going to go over them all now. Um, we should have seen them all. Now, you typically are only going to go from rectangular to spherical. You're never really going to be going the other way, right? The usual case is you have a function written in terms of x, y, z, and you're going to put it into spherical coordinates because you think that will be easier. So usually, I'll say that, um, usually you start in x, y, z and choose spherical coordinates because you think it will be easy. Or and so in that case, you don't need all of these, right? The only ones you're going to use are going to be the ones that convert from rectangular to spherical. So that's these, right? Because you're starting with x, y, z, and then you substitute those in. And also, you might use this one because if you see an x squared plus y squared plus z squared in your problem, you might want that. And that's probably what you're going to use. You're not probably going to use the other ones very often at all. So that's where we're starting here with spherical coordinates. What we want to do now is we want to try to come up with what's it called? How you might. Um, I'm missing a picture here. I'm gonna steal it. We do want this picture, so I am gonna go find it. Um, so the what you do want, I forgot what I was gonna say, but I'll find this and then we'll come back. Go, stop. Oh, I almost said a swear word, guys, but I didn't, and that's what's important. Please just let me get the picture. Just let me get the picture. I just want this picture. Okay. You know what's gonna happen here? I'm psychic, so I'm gonna tell you. So this is lagging really badly, making it really hard to just make this picture bigger. So what that means is now that this is done, I need to make it not laggy. So I back out of here. And when I come back in here, that picture is probably going to be gone. Just stay. Okay, it didn't. All right. So here's just a few common shapes that you're going to see in spherical coordinates. Right. So of course, in spherical coordinates, a sphere is just like this radius rho is a constant, right? Because you're measuring from the center out to the edge of the sphere, um, from there out to there. Um, and you're not making any restrictions on the angles, which means the angles are free to go, um, any angle around. So constant radius is a sphere. Then you've got a half plane where theta is just a constant, right? You know that theta is measured from here over to a line. And so theta equals a constant, looks like a line in the xy plane. It's actually half a line. That's why they say it's a half plane here. You have a half a line, and then the z value basically can be anything. And so you end up with this plane, half of a plane. You've got a half of the cone, which is going to be when the phi is equal to a constant, because of course the angle phi is just from the z-axis down, um, Always have the wrong color for showing up, right? Because that's how you measure phi. So if phi is a constant, then you measure down that angle, and then you're letting theta be anything, so that can rotate around 360 degrees, and you get that cone. And anything less than pi over 2 is going to be above the xy plane, and anything above pi over 2 is going to be below the xy plane, right? Because this is more than 90 degrees. So obviously this is more than 90 degrees, and this one was less than 90 degrees. The main thing to keep in mind here is just that these are the shapes that are easy to make with spherical coordinates. And when you have these shapes, this is often why you will be choosing spherical coordinates. So usually you choose spherical coordinates when you have some of these kinds of shapes. You have to integrate over shapes like these. Shapes. Like these. Okay, so that's just kind of just a reminder of what spherical coordinates are. If you want to set up a volume integral, then we need to know what that volume element is. So to set up a volume integral, right, that means triple integral. We need to know the volume element. For example, right? So in rectangular, you have dv is dx, dy, dz in any order. And in cylindrical, dv, yes, I will slide this over a little bit. Okay, dv is r, dr, d theta, dz, although usually we put the z first. We ended up integrating with z first, but that's just down to specific problems. And for spherical, I'll write it down here because why not? We will sort of see why this is true. I'm not going to derive this super well. I'm not going to really derive it at all. I'm just going to show you the picture. But the volume element is going to be dv equals rho squared. It's not a p, it should be a rho. Rho squared sine phi d rho d phi d theta. So you actually, like, this is extra for cylindrical coordinates, the r, and here you have rho squared sine phi. So that's extra. So that's quite, a difference. You're just going to have to throw that in to every integral that you're doing in spherical coordinates as part of the dv. But why? And so in order to see why, we're going to look at the picture. I don't know that this picture is great, but we will use it. Come on. Make it a little bigger. Okay. Well, okay. I have to move that down. All right. So when you're looking at, a spherical box, so to speak, right, this is what the volume section looks like, and they cut out one right here. And really, it's hard to see what's going on here, and so I'm going to try to show you at least two of the pieces here. So let's look at their picture, and I'm just going to draw on it. So let's see here. So first of all, this distance right here, right? We know that the way you measure rho is from the origin out to the point. So from here to here, the only thing that's changed is rho. So this is actually a delta rho, that dimension. Okay. Now another dimension is going to be this one right here. And that one is going to be calculated in a way that's similar to the way we calculated theta when we did the cylindrical coordinates version of this. You have a delta phi down here, right? That's measuring that. But you know that the further away you get, like this distance here is smaller than this distance here, even though the delta phi stays the same. And so this distance to this distance, in order to get that effect that the further away from the origin you are, the more, the longer this line swept out is that, you know, where we did that, like sector of a circle. I didn't use those words, but sector of a circle is like the radius times uh, the radius times the change in the angle. So here the angle was phi, so the radius is rho. So that's rho times delta phi is the same as r times delta theta when we did the cylindrical coordinates version. So those are two of them. And then for the third one, the one we're missing, right? We have this dimension as well. There. And so we'll use that. Um, so what they do is you are going to take this shape of the actual volume. Stop that, please. You take that shape for the actual volume, you project it down into the XY plane. So you get this kind of shadow here, right? So you get this kind of shadow. And then when you do that, what they're saying here is they're saying that in order to get this distance, that's not rho anymore. That's rho sine phi. And so if you want to do the equivalent of this sector of a circle, in general, right, we said it was rho times like the delta theta. So that's what it was for in polar or cylindrical. I'll just say polar. It was r delta theta. So this was the radius. This was the change in the angle. And we already saw one of them here was for the phi here. It was the radius was rho and the change in the angle was delta phi. And this one for theta, you have to come down here. You actually, in order to get this distance, you have to use this sign in order to project this down onto the plane. And so the radius here for theta, this is not theta equals, I shouldn't say that, theta. The radius is actually rho sine phi. I'm not going to derive that, I'm just going to say it. And then the change in the angle here was from here to here. That's the delta theta. That. So this question mark here for this distance turns out to be rho sine phi delta theta. Pretty complicated. But once you have those three listed down, you can multiply them in order to get the total volume of this thing. So if you write it out, right, the delta V is going to be the three colored things I wrote here. So you've got the, stop. So you've got the delta rho from right here. Then you've got rho sine phi delta theta, rho sine phi delta theta. That's the long one. And then you've got this one, which is rho delta phi, rho delta phi. And if you work this all out, you can combine this and this rho, and there's a rho there, and a rho there. So you end up with rho squared. And then you got your sine phi. Oops. Then you've got your sine phi. And then you've got your delta rho, delta theta, delta phi, which you can write in any order. So delta rho, delta theta, delta phi, whatever it is. Okay, and then that's your delta v. Okay, then just like before, if you want to figure out how to calculate a volume, the volume would be summing up three of these where it's the function of rho ijk, um, theta ijk, phi ijk, and then you've got your volume element, which is just all of this. All of that just goes right there. And that's what you're seeing here. You can't see that. This is what you're seeing here for the for each box. And I guess this row here needed to be ijk as well. So that's adding up, that's summing up a bunch of these. Okay, now like before, we're not actually doing any Riemann sums with these. This is just, you can go from the volume of a volume element like this to the sum of many volume elements like this. And then from there, you can take the limit as the I, the J, no, they call them L, M, N, right? The top limits here to infinity to get the triple integral. Okay. Now, of course, we don't actually use that for anything. We use Fubini's theorem. We just compute integrals with Fubini's theorem. Which, do I have Fubini's theorem? I don't know if they bother with it. Probably it's right here. Let's see. Yeah, look at that. So we've seen Fubini's theorem a number of times, and here it is again. So this is just saying, if you want to integrate a continuous function on a spherical box, again, spherical box means just all your limits are constants. If all your limits are constants, then the shape is something like this, right? It's not really... Man, Notability is really causing me issues today, more than normal. Um, it's just the pointer, so it shouldn't be doing anything else other than pointing right now, but it's moving stuff all around. Like this is a spherical box, right? The edges are actually curved. This one's bigger than this one. This top one is actually the like a small section from a sphere, and so on. So spherical box, right? When all of the variables are just between constants. Okay, and as it says, you can integrate with respect to the variables in any order when it's constants like this. If it's functions, of course, it's more complicated for a general region. Okay, so having said that, we need to just practice this and we'll see how it goes. So here's our first problem. I don't like that one. Okay, yeah, we'll do that one anyway. Homework. This is from the homework. Example. Evaluate integral, they go theta from 0 to 11 pi over 6. Sure. Phi from 0 to pi over 3. Rho from 0 to 1. And then it's 4 rho to the 7th sine squared phi. d rho, d phi, d theta. Of course, the order makes sense here, right? D rho, and this is rho, then theta or phi, then the middle one's phi, theta's last, this one's last. Okay, and so the actual evaluation of this integral is the same as any of the other integrals you've done. You're not really making any kind of, nothing is new here as far as how to evaluate integrals. So we start with the most inside integral. So if we were going to integrate this, right, we just need the antiderivative of this, but specifically we're doing the d rho integral. So we're really just looking at that rho to the seventh, right? So what's the antiderivative of rho to the seventh? It would be rho to the eighth over 8. So you'd have 4 rho to the eighth over 8. And then you're just dragging along the sine phi with you. And then you've got your d phi, d theta. And rho is going from 0 to 1. So integral 0 to 11 pi over 6, 0 to pi over 3. Of course, this is 4 over 8, so that's actually just 1/2, or rho over 2. We're putting in a 1, so that would be 1 to the 8th over 2 sine, this should have been sine squared phi, minus 0 to the 8th over 2 sine squared phi, d phi, d theta. So when you work this out, of course, we're doing it by hand now. When you work this out, this one's going to be 0 because of the zeros. This is going to be 1/2 sine squared phi, 1/2 sine squared phi. Then you've got d phi, d theta. And so now you've got to integrate 1/2 sine phi. So the only real problem that you're going to have with integrating stuff in spherical coordinates is stuff like this. Powers of sine are going to show up pretty often. And so what you're going to want to do is just keep note of certain trig identities that are going to show up a lot. So like trig identities, purple math, I think that one's good. And so you want the one that's going to bring that power down. So here they are, right? These are what you're going to want. So these identities right here are exactly the ones you want because they're going to bring the power down in that sine squared. So you'd go 0 to 11 pi over 6, 0 to pi over 3. I can take that 1/2 out. Nope. And then sine squared phi, of course, is going to be 1/2 1 minus cosine 2x. So for us, it's going to be 1/2, write it here, 1/2 1 minus cosine, not 2x, 2 phi, because that's our variable, right? And then d phi, d theta. So you're going to need that kind of identity pretty often. And once we got it, we're going to do what? We may as well, let's just take this 1/2 out with the other 1/2 and make that a quarter. So you have 1/4, 0 to 11 pi over 6. Let's actually integrate. So what I did here was I took out the 1/2, so that 1/2 is gone. So we're just integrating 1 minus cosine 2 phi. So the antiderivative of 1 d phi is phi, and the antiderivative of cosine 2 phi is going to be, sine 2 phi over 2, right? And then this is going 0 to pi over 3. We've got a d theta. So 1/4 here on the outside. Still, we have to plug in pi over 3. So we have pi over 3 minus sine 2 pi over 3 over 2 minus 0 minus sine 0 over 2 d theta. Luckily for us, right, that's a 0, that's a 0. Always like it when that happens. You need sine of 2 pi over 3. I think that's square root 3 over 2, right? If you don't know, then you check a calculator or something, but I think it is. I'm just going to check it because I'm tired of making mistakes on these. Oh, well, I just turned it off, so I'll just trust myself. I changed my mind. Right, of course it is. Of course it is. So we have one. Hey, why am I pink? 1/4, 0 to 11 pi over 6, pi over 3 minus square root 3 over 2, positive uh, d theta. So what are we going to do here? These are not like terms in there, the pi over 3 and the root 3 over 2. So I can't really simplify that. I just need to do the antiderivative. So the antiderivative here, may as well just keep those in parentheses and just add a theta. 0 to 11 pi over 6. So you got 1/4 pi over 3 minus root 3 over 2 theta, which we're going to multiply by 11 pi over 6, minus pi over 3 minus root 3 over 2, 0. That's all 0. So we get what we get. Guess we can simplify this out maybe a little bit. What would we get here? So I guess I'm going to leave that 1/4 on the outside for the moment. If you multiply this by this, you would get 11 pi squared in the numerator over 18 minus, and then here you would get 11 pi root 3 over 12. And then you'd have to multiply that 1/4 in. So that would be 11 pi squared over 18 times 4. 18 times 4 is what? 72, right? 18 to 36. 36 times 2, 72, I think. Minus 11 pi root 3 over 48, I guess. So there we go. This is a good opportunity to make sure that we still know how to use Wolfram to check our answers, right? Before you type it into the computer. Just go Wolfram. And again, the way I do these is I don't use the calculators, although you can. So do what you want for the variables. Like I can use, um, like I'm using p instead of rho. And then for phi, I've got to do something. I think I'll just type in phi or phi. And then we got dp, d phi, oh, actually just that. Okay. So just d rho. And then we were integrating from 0 to 1. And so I can do that integral there, and then I can just compare it to the answer that we get, which is supposed to be sine phi over 2. So we look here, we say, did I get, um, what happened? Oh, right, because I did the integral. Okay, so the end result there was 1/2 sine squared. I got 1/2 sine squared. Um, oh, because I didn't put the squared here. Try again. Okay, sine squared over 2. So I got sine squared over 2. And then the next integral, right? The next integral to do was this one that you see. We're supposed to integrate that from 0 to pi over 3. So I just click on it here. Um, well, that's sneaky. They have the actual symbol there. How am I going to get that symbol? Can I copy that? Copy. Okay. So then I can go integrate that. Oh, I can just do like, I could just type phi again, but um, what I just do? What just happened? Okay, so integrate that. Sine squared phi over 2 uh, from 0 to pi over 3. I don't know why I wanted to just copy paste that symbol. I was just happy to see it. Um, all right, so you see there that we get the answer there. You get 4 pi over 48, which is, pi over 12. Do I have a pi over 12? Where's my result? Oh yeah, see, look, right? I put the quarter on the outside, but a quarter times pi over 3 is pi over 12. And then you got 3 root 3 over 48 would be, um, is there a mistake there on mine? Huh. I might be catching a mistake here because uh, they've got, was it pi over 3? So already a 2. Because they have 3 root 3 over 48. And I've got root 3 over 8. So 3 over 48 is not 1 over 8. So I've got a mistake here, don't I? Let's see what I do. So how did this happen? See, this is why you use Wolfram Alpha to look for these kinds of mistakes. So I had 1/2 here, took that out, so that's gone. So this is right. Um, then I wanted to integrate this. So I integrated this. This is going to be cosine 2 phi is going to be sine 2 phi over 2. Okay. And then, see, it is a mistake because this is square root 3 over 2, but then there's another 2 there. So this should have been a 4. So see, this is why you do this before you type stuff into the computer if you're worried about your score. So this should have been a 4. So these all should have been 4s, like that. I mean, so should this one over on the right, but we don't care about that. So then when you do this, it's not 2 times 6, which is 12. It's 4 times 6, which is 24. And then when you come over here and you multiply that by 4, 24 times 4 is going to be 96. So I think I fixed it, but there we go. So now let's go back and see if we can finish this integral off. So they did this. They got 1 over 48 there. So then I'm going to come back to the beginning here. I'm going to type integrate. And there's only there's no variables here. So it's d theta though. And we're going from 0 to 11 pi over 6. And they have that, which is 0.88436. And that's written a little bit different than mine. But if you look how they wrote it, if you do that, like you see the 288 in the denominator, if you do 4 divided by 288, you get 1 over 72. So that matches my first constant there. And then if you do 3 over 288, you get 1 over 96, which matches my second constant in the denominator. So that does work out. Okay, so you can do that. Of course, you can also use the spherical coordinates calculators, but you need one that's in spherical coordinates triple integral. So you'd have to Google triple integral spherical coordinates. And that's just the fastest way to find the calculator on Wolfram if you want Wolfram. So I didn't type in calculator, but there. So you can find the widgets. And like the polar coordinates one, you don't, oh, you do get to change the order here. Look at that. The polar coordinates one didn't let us, remember? But this one does. So this one's better. And probably you can use the variables in the limit. So I can put like a phi there, and I could put like a theta there, for example. And if the integral is doable, I probably ruined it, but it's okay with having the variables and the limits of integration. Probably you can do it though. So again, if you want to do those, you would have to Google for the calculator, because if you just go straight to Wolfram and you go like triple integral spherical, sometimes you can find things this way. And sometimes you can't, right? Like you don't, like this didn't actually find the calculator for spherical coordinates and that kind of thing. So that's why I've been saying Google it if you want the calculator. Don't just do it in Wolfram. Just trying to make Notability work again. Black screen, that's always good. All right, so that's back. So we did one of these integrals. I see that they wrote their answer exactly the way Wolfram Alpha did. Wolfram Alpha probably uh, calculated it. Okay, let's try to set up an integral. So this is off the homework again. So they say, consider the region B, B for ball, which is a ball of radius 11 centered at the origin with a function f rho theta phi. Okay. Oh, well, they say set up a triple integral. Come on. Okay. So we're just trying to set up an integral over the ball. So the idea here is pretty simple. Um, so you got the ball centered at the origin with whatever radius it is. And so the thing about spherical coordinates is that um, a sphere is just a very simple function. It's just rho, right? But in order to integrate here, what you would do is you would say, okay, well, the variables are, you have rho, but we want rho to be the entire inside from 0 out to that sphere. So rho should go between 0 and 11, right? Because it's out at radius 11. And then for phi, or yeah, we'll do phi, straight up, right? Straight up is phi equals 0. Straight down is phi equals pi. That's as big as phi gets, is pi. That goes out to pi. So when you integrate like just those bounds here, what you're thinking of is, right, like we're going from out here to straight up here. Whoa, I didn't know I could get an arrow. And then integrating all the way down there. So you feel like you're integrating over a half sphere. But the thing is that's actually, we're going to let theta go all the way around a circle. So like this can go all the way around, and you can think of this region here being rotated all the way around the circle, and then that will sweep out the entire ball. Okay, so these are what the bounds of a circle with radius something look like. Okay, so every ball centered at the origin has limits that look like this. Okay, so you should get used to this kind of thing. Like specifically, phi goes between 0 and pi, theta goes between 0 and 2 pi. Those are like the all possible theta, all possible phi values. And then for a sphere, we want to go from radius 0 out to radius whatever the sphere is. And so when you go to set up this integral, then it's actually pretty easy. They start with they start with theta on the outside. So you go 0 to 2 pi. Then they do phi in the middle, which is going to be 0 to pi. And then they've got rho on the inside, and that's 0 and 11. And the integral would be integral of rho theta phi. And then you've got, you have your volume element, which is rho squared sine phi d rho d phi d theta. Got to get those in the right order to match your integral. And that's it. And remember, all of this is just the dv. So that is the integral. So that's the answer there. So pretty straightforward when you're integrating just over a ball. A ball is the easiest possible region to integrate over. Okay. I see another integral exactly like the one we did in the homework. Oh, okay. Yeah, let's do this. So what if you have a related question? What if you have one like they say, let B be the top half, they say above the xy plane of a ball centered at 0, 0, 0 with radius 5. Set up a triple integral over that B. Okay, so it's the same deal as the previous one, right? You've got a ball, but of course the difference between the previous problem and this one is that we don't want the entire thing. We only want the top half of the ball. Okay, and so everything's the same, but in order to get the top half, what you do is, if you remember phi equals 0 is there, phi equals pi over 2 is there, right? 90 degrees. So you just want this section for phi instead of that section, right? So 0 to phi, 0 to pi over 2, 0 to pi. So if you want to leave out this bottom section, you just leave out the section where phi is greater than pi over 2. Other than that, it's the exact same setup as the previous problem. So rho would go 0 to 5 because that was our radius of the sphere. Phi goes 0 to pi over 2. That's the only difference. This is the only difference for the top half of the sphere. And then theta, we do want all the way around that. So that's still going to be 2 pi. So, right, that's all we have to do. So if we're going to set up that integral, then the integral would be exactly the same as the integral that we did in the previous problem. All you got to do is change the radius, and also phi goes to pi over 2 now. And now different sphere radius and only the top half. So again, the reason we're using spherical coordinates is because spherical coordinates is easy for spheres. Okay, let's try to do one that's a little more complicated. Um, so they give us a picture. I'm going to use their picture. Oops, I should not keep doing that. Anytime I leave the anytime I leave notability, bad things happen, right? Leave. Oh, hey, we're not in presentation mode anymore. Oh, it actually just force closed. That's awesome. Oh, now we're back in presentation mode. How much did we lose? Oh, nothing. Okay, good. So if we say set up an integral for the volume of the region bounded by the cone, z equals square root 3x squared plus y squared, and the hemisphere, which again just means half of a sphere, z equals square root 4 minus x squared minus y squared. Okay, and there's a picture here, but before we do the picture, I just want to make like a comment here. Maybe I should have done it before this, but actually we'll do this. I'll move that down. Um, Move it down further. Okay. So just a comment, you're not really going to have like top surface, bottom surface integral of the shadow on the xy plane anymore. Um, so um, so this is just kind of a note. Um, if you've got like a surface here, for example, so like let's say this is rho equals a function of uh, I don't know which one they write first, theta, and then phi. I don't want f. Say u1. And then out here, you have another rho equals u2 of theta and phi. So notice it's not like bottom and top anymore. It's inside and out compared to where 0, 0, 0 is. Um, just move this a little bit. Yeah, that's good. Okay, so these are like surfaces, right? So these are just surfaces in space. I don't know what those lines were indicating. Then when you set up your integral, the idea is you've got some kind of bounds here. So you have like bounds for phi like that. And I was trying to draw this so like it was kind of fitting in there good. Okay. Um, and then yeah, and then your volume that we're integrating over is supposed to be between these two, right? If you've got this kind of thing going on, then what your integral would look like is you do, just get out of the way. What your integral there would look like is your first integral that you set up, the inside one, would be from rho equals this one, the inside radius. So like u1 theta phi to rho equals u2 theta phi, like that. So you have an inner radius and an outer radius, so to speak. But like, and then if you do an integral for phi, the way I drew it just with constants phi1 to phi2. So it'd just be phi1, phi2. I wrote theta, but phi. And then your theta would be, well, I didn't really indicate where that would be here, but, you know, some kind of whatever was appropriate for the problem. The thing that I was trying to get across here was really that um, there's no top and bottom surface, but there's an inside surface and an outside surface. And then, your other variables are just going to have probably constant bounds, but not necessarily. And I just wanted to mention that because when we're setting up the integral here, what's the picture look like? I think we have it. I can paste it. This is what the picture looks like. It was given in the problem. They say the volume of the region bounded by the cone and the hemisphere. So specifically, what do they want? They want, um, let me see here. Oh, well, it's annoying. They're not doing what I thought they were doing here. We don't need to know this in order to do this problem. So the area they're talking about the area between the cone and the sphere. So specifically, they're actually just talking about like this area or volume, but you know what I mean, right? So they're specifically talking about the area between the cone and the sphere. So this area, volume, right? Also on the other side. Um, and so I guess the red is indicating that we're not integrating that because that's inside of the cone, and we're integrating between the cone and the sphere. Okay, so that's what they've got going on here. And so the way you would deal with that is as follows. Well, first of all, we need to know the equations of those two surfaces, the cone and the sphere, right? So let's start there. We would need to know, I guess technically we don't, but of the cone and the sphere. And that's why we looked at those pictures before, so we could, hopefully figure that out. Um, but if we don't know, right, we can go z equals square root 3x squared plus y squared. Right, that's the one that they've got labeled right there. What would that be? Well, what's x squared plus y squared? So I don't know why I wrote the z there. So if you go up to your conversions way up here, right, here's your conversion. So x squared plus y squared is nothing in particular, but it would be um, rho squared minus z squared, right? So if you solve this for x squared plus y squared, stop. Why won't you just let me write? Um, Rho squared minus z squared would be x squared plus y squared, right? And then what is z? Z is rho cosine phi. So this would be rho squared minus rho cosine phi squared is x squared plus y squared. Just by rearranging this and plugging this in. So I'm just going to actually still this, come down to our problem, takes forever to scroll. And what we're going to do is we're going to try to plug that in and hopefully simplify that. We could have just done this in an easier way where we actually just looked at the pictures of those shapes and done this quicker. Because this is what I got. So I've got this right here. So this would be 3 um, rho squared minus, and you square this. So rho squared minus rho squared cos squared phi. So that's, you could square root 3 rho squared 1 minus cosine squared phi, like this. You could square root 3, and the square root of rho is just rho. Then you got square root 1 minus cosine squared there. What's 1 minus cosine squared? I think, what is 1 minus cosine squared? Right? We need trig identities. Do we have those? No, of course not. Right, we already looked at it once, but I'm just bringing us to it. Um, so we have 1 minus cosine squared. Um, wait, what is 1 minus so? Wait, why are we looking this up? We don't need an identity for that, right? We know that sine squared x plus cosine squared x is 1, right? So if you move, so sine squared is 1 minus cosine squared x. So this is square root 3 rho square root sine squared phi. So it's square root rho sine phi. Okay, so we did that. And I guess we know that um, we don't need plus or minus or anything because from the picture up here, the cone is above 0. So there's not, because the cone is above 0, that means the angle is between 0 and pi over 2 for phi. And sine phi would then be positive, and so there's no need to worry about pluses or minuses or absolute values. Sine phi would be positive, so if you square it, you square root, you get back to where you started. So we get this square root 3 rho sine phi. Um, okay, so that's the cone. Actually, that's not, I do not like this. Oh, sorry. I did this. This was all just this side of the equal sign, right? The other side of the equal sign was z. Um, so, sorry, let me erase this. Sorry, I'm going to rearrange this here. Okay. We had that z the entire time, right? But at some point we should have substituted in what z is. What is z, by the way? Right? I know we said it, but we have to look it up again because I forgot it. Z is rho cosine phi. Rho cosine phi. So you come down here, you go, z is rho cosine phi, dot, 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 rho cosine phi, like that. And then what can we do? Let's just move, like divide everything by rho cosine phi, rho cosine phi. On the left, we just get 1. On the right, the rows cancel. You get square root 3, and then sine phi over cosine phi is tangent phi. So then you divide by the root 3, you get 1 over square root 3 equals tan theta. And you could actually just find, whoa, about tan phi. So phi is going to be tan inverse of 1 over square root 3. And tan inverse of 1 over square root 3, do that on a calculator or something, and you get pi over 6. And that's a constant. And the reason it's a constant is because this is just pi over 6, that angle. Stop moving pictures. I don't want to move the pictures. I wanted to write on the picture. So that angle is just pi over 6 there, turns out. There were other ways to get that. Maybe we can talk about those. Um, Another way to get that would be to figure out one point, like to figure out a point that's like right there, that's on both of them. And then once you have that point figured out, you can go to a diagram like this, figure out the x, the y, and the z, and then you could actually just figure out what that angle is using trigonometry directly without doing all of this substituting stuff in. But you should not be surprised that you end up with a constant here, because remember, we looked at the pictures, and according to the pictures, we knew that it should be phi equals a constant, is what a cone is. So the only question is, what is that angle? And so any way you can find that angle is fine, but we got the angle by actually just putting in the conversion factors for all the variables here, for z and for this side, and then just working it out until we eventually had a number. Okay, so we did all that. What about the sphere? Probably the sphere is going to be a little faster, right? So the sphere here, they say, I mean, it's right here. You can just look at this picture and just say, like, from the picture, isn't it just rho equals 2, right? Sphere radius 2 centered at 0, 0, 0. Isn't that what this sphere is? Yes, it is. If you want to convert it, we may as well, just because we haven't done very many of these yet. So I'll just convert it, but we're going to get rho equals 2. 4 minus x squared minus y squared. So this is z. We just did that. Z is rho cosine phi, square root, 4 minus, it's 4 minus x squared minus y squared, but minus x squared minus y squared is minus parentheses x squared plus y squared, which is this. Rho squared minus rho squared cosine squared phi. So we have rho cosine phi equals what happens here. What is going to happen here? Oh, never mind. I don't want to do it this way. I'm changing my mind about how to do this. The way to do this is going to be to square both sides. Z squared equals 4 minus x squared minus y squared. Move the x squared minus y squared over. So you end up with x squared plus y squared plus z squared equals 4. Then, of course, this is rho squared equals 4. And then that's rho equals 2. Plus or minus 2, but by convention, rho is positive. So rho equals 2. Okay. So these are the two things. So how would we set up this integral then? Well, it's not as hard as you think. So just I'll draw my own picture because it'll be helpful, I believe. So the key here is to make sure, like they colored so much on that picture that it makes it hard to understand, I think. Whoa. Half circle. Come on, just give me a half circle. Okay, well, fine. Okay, so what's going on here is this. So you've got this. This is pi over 6, right? That's where the cone is. And then we only want this section, right? Of course, we want it all the way around, but we want this section. So when you're setting up this integral, it's very similar to the one that we've already set up. Like the row still needs to go from here to here. We're still integrating row from 0, in this case, to 2. Okay? Um, but your phi is going to be different, because if we want this section only, well, up here is pi over 6, down here is pi over 2, right? So what we want is, this is our bounds for phi. Nothing here, then we start at pi over 6 and we go up to pi over 2. So that's the only thing that was new here, actually, was we wanted to leave out this intersection. So, so we want phi between pi over 6 and pi over 2. The row we know is 0 to 2 because we're actually just integrating from the origin out to the sphere again. It's really the same kind of integral we've already done. And then our last integral for theta, well, we are going all the way around the circle again. So that's 0 to 2 pi. And really, I mean, this is like, took me a long time to do it, but the point here is that what we saw in these examples here was, first of all, if you're integrating over an entire sphere, then it's 0 out to the radius of the sphere, phi between 0 and pi, theta between 0 and 2 pi. And if you're cutting out part of the sphere, there's a good chance that all you're doing is limiting your phi value. So if you want the whole top half, you go 0 to pi over 2. If you want to cut out this center section and just do the outside, well, that's not 0 to pi over 6. That would just be inside the cone. We want pi over 6 to pi over 2. So that's what we did. So anyway, I hope that was helpful there. So this is, and then we would integrate. It would be rho squared sine phi d rho d phi d theta. And of course, I didn't say it, but of course, the volume of a region, I'll say E, is given by volume equals the triple integral of just dv, right? We used that in the previous 2 sections, and we're using it again. So that's why we just integrated this. There was no f because we're just calculating a volume there. Okay. So what I am doing now is I'm just clicking through some questions here. I'm going to get to some other spherical coordinates questions in your homework. Stupid confetti takes so long. Okay, this is cylindrical coordinates. We did those yesterday. Cylindrical coordinates, we did those yesterday. Give me a new question, guys. Cylindrical coordinates, we did those yesterday. All questions we've seen before. Cylindrical coordinates, we did those yesterday. Yay, we completed 3 of the topics. Okay. Well, oh yeah, let's try this. This is starting in rectangular, so it's at least different. Example. Use a triple integral to find the volume of the solid B equals XYZ It says spherical coordinates. I didn't write that, but a set of x, y, z such that 4x squared plus 4y squared plus 4z squared less than 72. Oh, it looks like a ball. Oh well. Y less than 0, z less than 0. So that's going to be maybe a different section of the ball than we're used to. Okay, so let's try to imagine what the shape looks like before we set up the integral. So first of all, 4x squared plus 4y squared plus 4z squared less than or equal to 72 is x squared plus y squared plus z squared. Divide the 72 by 4, and I think we get 18, right? That. So what that tells me is that this is a sphere with radius square root 18. So it's not like perfectly nice sphere, but a sphere. Now, so we got a sphere. Okay, so there's your sphere. But then they tell us that the y has to be negative. So actually, the y has to be negative. So if we have x here and y here, then what we're doing is we're essentially, that's not quite what I wanted. That's also not quite what I wanted, but it's close enough that I'll just take it. Um, so if we want the negative y's, right, we have y greater than 0 over here, y less than 0 over here. So we're already limiting ourselves to this section of the graph up to up to this plane. So we're just in the left half of that. But then they say z has to be greater than 0. So of course you have z greater than 0 up here and z less than 0 down here. So then you've got to cut out it really likes drawing rectangles, except when I want to draw a rectangle, and then it likes not drawing rectangles. So if we want z less than 0, then actually it's not even that area. It's only going to be um, this section here, right? So this is the section that we're talking about. Okay, so if that's the section that we're talking about where the z is negative and the y is negative, then what we do is this. So we're integrating from, it's basically the same. Rho equals 0 is here, and then rho equals square root 18 is out there on the sphere. So rho in between 0 and square root 18, that's just going to be origin out to the sphere. Okay. Now for phi, what angles do we need for phi? Well, again, that's where you got to remember what phi is, right? So remember, you're measuring from the, phi measures from the positive z-axis. So this top half is phi 0, phi pi over 2. The bottom half is pi over 2 to pi. And it doesn't matter whether you mark it over here or over here. 0, pi over 2, pi. So if you want the bottom half, we're going to need pi over 2 to pi, right? That'll be there. But then also we only want this section of the graph. So that's where we'll have to figure out for theta what's going on. Something else is going to happen to cut it out into that section. So if you look in the xy plane, right, what we're looking at in the xy plane is only the negative y value. So if you just imagine that circle again, looking down on this, then we only want this section. So that would be if we're measuring 0, pi over 2, pi, 3 pi over 2, back to 2 pi, right? Then we would want from here, and then we would want all the way around. So in order to only be calculating the area where the y is negative, we would need the theta to go from pi to 2 pi, like that. So that's origin out to the sphere. This is going to be the bottom half, and this is going to be the part where y is negative. Okay, and then once you have those down, of course, then you can just write out the integral, because you can go theta goes from pi to 2 pi, rho goes from pi over 2 to pi. I said rho, phi goes from pi over 2 to pi. Rho goes from 0 to square root 18. And then they say the volume, so the volume would be the dv, but that's rho squared sine phi d rho d phi d theta. And we can just calculate this. We're going to use a computer because we've done enough integrals like this one. Oh, we got a widget. Should we use it? So I don't know if we have to type in the rho sine phi here. So I'm just going to leave that blank. I'm going to put a 1 there. And then rho from 0 to square root 18. We'll look at the result and we'll see if it makes sense. Phi from pi over 2 to pi. Theta from pi to 2 pi. So we'll have to check if it added the rho squared sine phi for us, or if we were supposed to add it ourselves. No, you know, rho phi theta. You don't want to do it? Okay. Well, I guess we'll just go to regular Wolfram alpha then. I'll type it rho squared sine phi d rho d rho. All right, so we're integrating. Integrate rho squared sine phi d rho from 0 to square root 18. We will get something. We get, why is there an O? Oh, because I typed in an O. Okay. All right. So 18 square root 2 sine phi. So I'm just clicking on that. We know what to do with that. We're going to integrate it from, oh, actually, let's say d phi from pi over 2 to pi from my second integral. Did it? Okay, I typed it in wrong, but it still figured it out. And we got a constant there, but we still have to do one more integral. Theta from pi to 2 pi. So with that, just going to add a pi d theta from pi to 2 pi. We get 18 square root 2 pi, and this was a volume, so it should be units cubed. I'm just going to type this in, get it right, 18 square root 2 pi. Submit. Yay, we got it. Okay, so yeah, they do a lot more work, by the way, in the book for this. But so you do want to have this idea that when you're integrating over a section of a sphere, that's kind of the normal thing that you're doing, and they're just going to make you cut out different pieces of the sphere depending on whether y is positive negative, z is positive negative. X could be positive negative, right? You're just going to get like different halves of the sphere or different orders of the sphere or whatever. um, oh, okay. One more example. Set up an integral to find the exact volume uh, outside the sphere 7x squared plus 7y squared plus 7z squared equals 36, and inside the sphere x squared plus y squared plus z squared equals 6 with y greater than 0. Now, okay, this is badly worded because I don't know if the y equals 0 applies to both spheres or just the one sphere. So I'm going to actually do a cheat here on the thing and look at what the result says. Um, to see what they meant for us to do. Where's the integral? Okay. Phi, they have 0 to pi, so that's okay. Y positive. No, that's phi. Phi positive. Okay. What? Oh, okay. Yeah. Okay. Good. So this applies to the whole thing. I didn't know if they just meant like we were cutting out half a sphere from a full sphere or what. Um, yeah. But here's what's going on. So they've got. I mean, it's just exactly what they said, but there's just two spheres. So you have this sphere, which they say is the smaller sphere. It has the bigger numbers, but that's because they have numbers on both sides of the equation. So stop erasing. All right. So you got a small sphere. So this is the small one. So this is the equation 7x squared plus 7y squared plus 7z squared equals 36. Then you have a larger sphere. Okay. So the larger mm, So the larger sphere is x squared plus y squared plus z squared equals 6, right? Is it 6? Yeah. So you have that. So they want the volume in between them, but also only in the part where the y is positive. So if we just kind of just put it there. Okay, that's a rectangle. Okay. I can't guarantee that this will look okay when I try to shade, but so what they want is they want the area between these spheres, but only in the part where y is positive. So, right, y is right here, x is here. So they want the area between the spheres there. Okay, so what you're doing is this is where you do need this idea that we talked about previously, where you're going to have um, like from 0 out to one of the spheres and then from 0 out to the other sphere. Um, that's this kind of picture. So this is your inside sphere and this is your outside sphere. So what you're going to use for those is you're going to have them set up so that those are your bounds for rho. So inner radius, outer radius. That's what you want to think of this. So when you see this, that's what you're thinking. So like we know that rho is going to be between from the small sphere and then out to the big sphere. Okay. Now for phi, phi is measuring from, from straight up to straight down, right? 0 out to pi over 2, that'll only get the top half. We do want the bottom half, right? Top half and bottom half. So that means we're going to have the normal limits for phi, 0 and pi, right? Pi is the biggest that gets. And then for theta, again, we're dealing with y greater than 0. So you kind of look at the xy plane just to remember what's going on there. We can just think of, you got this kind of thing, but then you got this kind of thing. Well, I should have at least managed to make them concentric. Try to put that. Okay, cool, good. We only want the section down here, right? And so just like before, wait, no, they said positive, right? Y greater than 0. So y greater than 0 is actually this part. So in terms of theta, of course, this is theta equals 0. Out here is theta equals pi. So we want theta to go between 0 and pi as well. In the previous problem, it was the bottom half, and that meant theta should be between pi and 2 pi. But here, y is positive, so it's 0 to pi. So all we really need there is big sphere and the small sphere equations. And there's not really that much to do with those, right? The big sphere is x squared plus y squared plus z squared equals 6. So that's rho squared equals 6. So that's rho equals square root 6. Your small sphere was 7x squared plus 7y squared plus 7z squared equals 36. Divide everything by 7. Like that. And then that's rho squared equals square root 30. No, just 36 over 7. And then you square root. So rho is 6 over square root 7. Okay. So when you go to set up your limits, you use those for rho. So our integral, theta is going 0 to pi. Phi is also going 0 to pi. And then rho is going small sphere to big sphere. So that's rho goes from 6 over square root 7 to square root 6. And then it's a volume integral. So you're just integrating rho squared sine phi, and then d rho, d phi, d theta. Okay, so that inner radius, outer radius thing is something that you have to at least have some understanding of in order to get your bounds for rho in a problem like this, where they say inside something, outside something. Um, the reason we didn't have to do it up here on this one was because actually from the origin out to where we were integrating, there was nothing in the way. So even though there was a surface here and a surface here, you never actually had to go through two surfaces, right? You didn't have to integrate, like there was no hole in the middle. There's a hole, but it's not like in the middle of this section. So that's why there was no inner radius, outer radius there. And there is here where there's obviously a big hole in the center. Okay, let's see here. Another one that's identical in the homework. Oh, they actually make you do the integral or not. That one's a constant. You can integrate between constants. That's constants. You can integrate between constants. Okay, I think that's it. I'm just going to click one or two more questions just to make sure there's no surprises. No, there aren't. So mostly your problems in the homework for spherical coordinates are ones that you've seen here. So in between two spheres, you have to do a few times. You actually have to integrate them a couple times, but you know how to integrate this now. Um, you do have this issue of sometimes, y is positive, so like sometimes y is positive, sometimes y is negative, sometimes z is positive, sometimes z is negative, and so on. Um, and I don't think this cone thing actually appeared in the homework. That was from the textbook. So I think your homework questions are actually easier than the textbook questions in this section. So anyway, that's it for now. Good luck on your homework and come to office hours if you have any questions.